relay setting and protection coordination. This video will cover related to the manual calculation of relay setting for motors, for motor circuit breaker, for incoming switchboard, incoming circuit breaker. With the help of ETAP software also we will validate. So let's start. So if you see, this is the one typical ETAP diagram, ETAP single line, one line view. Here this grid is connected 132 kV grid, step down to 33 kV, further step down to medium voltage 6.6 kV, and LV low voltage is 415 volt. So what we will do, we will start the protection coordination, the explanation and validation with this ETAP software. Let's see, suppose for this 75 kilowatt motor, so in this video I will try to cover all the protection related settings and coordination for this low voltage motor, 75 kilowatt motor, which is connected through a circuit breaker from LV switchboard 415 volt board. So let's start this. So I have modeled here this 75 kilowatt motor. So what are the parameters required? Let's see. So this is 75 kilowatt motor, and here the full load current is 123.5 ampere. Lock rotor is 600% of motor full load current, that motor full load. So lock rotor current is coming 741.2 amps, 741.2 amps. So during motor starting condition, we need to consider, whenever we are going to set the relay and the protection coordination purpose, we need to consider this starting current as well. This is one important parameter, and the motor nameplate rated current, which is 123.5 ampere. And one more parameter, you can find it here under load tab. You can define here, this is for actually for static motor starting, so no need to define here. You can go to protection tab over here and specify the motor acceleration time here. So let's say this is motor starting current. Let's say this is taking 3 second time to start the motor at 100% voltage. Okay, and now let's go simply to the start view mode, and here you can see this is create start view. So we can create the TCC curve, clicking here. So whenever you are coming to this TCC curve, this is TCC curve, and here this is the online view equipment diagram. You can bring it to here also. You can increase or decrease the size. Okay, so you can create the grid view as well. This is grid view. So for the better clarity, let's turn off this grid view. Okay, so now here what we can see, we can say here this is the motor starting curve in TCC here at 100% voltage level. Okay, now let's better understand keeping the TCC curve side by side. Okay, so during the protection relay setting protection coordination, we need to specify the motor starting time at 100% voltage and also at 80%. So at 80% motor terminal voltage, let's say the motor starting time is 5 seconds. Just notice here what are the changes are coming. Okay, so this is at 80%, this is at 80% motor voltage, motor terminal voltage. If you uncheck this box, this smooth corner will be removed. If you check this one, the corners will be smooth. What is this asymmetrical factor? This asymmetrical factor is during the starting condition, motor starting condition, due to the asymmetrical current, because you know the pure sinusoidal curve may not be available during starting of the induction motor. So this is the asymmetrical factor. Because of this, you can make it 1, then this line will be straight, this will be one straight line only, and if you apply this 1.6, then asymmetrical factor, then the curve will not be a straight line. And also one more important parameter is here the thermal limit curve. The thermal limit curve, there are two: hot thermal withstand curve and cold thermal withstand curve. Let's say this is 14 seconds, and also the cold, as you can see here the curve is generated, and here let's see this is 16 seconds, another curve will come. So this is for cold. So now we have created the motor starting time at 100% motor terminal voltage and also at 80% motor terminal voltage. We have applied the asymmetrical factor of 1.6. We have defined motor thermal withstand curve. This is hot start and cold start. So these parameters are required to define a motor in TCC curve. Let's click OK. Let's have a closer look here. Okay, if you want to differentiate, how to differentiate, this is 80% and this is 100%. Let's double click here, go to the devices, go to starting 100%. Suppose I want to give this color, and also I want to change the thickness 1.4. Okay, so now it will be understood in a better way. So now our motor is as per the modeled motor. We have defined all the motor parameters with this thermal withstand curve, also hot and cold withstand curve. So now let's move to the main part. For this motor protection, we need to coordinate, so that protection should come in between the motor starting curve and this hot withstand curve. So in between this, we need to place the protective device to protect the motor from overload or short circuit. So this upper part will be responsible for the overload protection or overcurrent protection, and below portion this part, this will be the short circuit protection. So let's go back. Okay, so to protect this motor, and first of all, this is connected with a cable. This cable size is single run 3 core 150 square mm. So this motor is protected by, let's say, circuit breaker MCCB. So let's define and coordinate this circuit breaker to protect this motor. Okay, here is the rating. What will be the rating? So before that, let's check once again the motor full load current. The motor full load current, what it is drawing, the motor full load current is 123.5 ampere, 123.5 ampere, and also the motor starting current is 6 times of rated current, which is 741.2 amps. 741.2 amps starting current, and rated current is 123.5 amps. So what should be the circuit breaker rating here? Go to the rating page. Let's select this as MCCB, not air circuit breaker. Let's see, this is molded case circuit breaker. Let's go to the library. So let's select from a standard manufacturer. Suppose I want to choose from ABB manufacturer and one model. Suppose this 160 ampere X4B model, because the motor full load current is 123.5 amps. 123.5 amps, so we can choose this 160 ampere. 160 ampere 3 pole, and here 415 volt level, short circuit data, and size I will select this 160 amps. And so this is related to circuit breaker, what we have defined till now. And let's define the trip device also. Let's select solid state trip. So this is the trip device specification we need to specify. So we will select the release feature. Release feature is available. This is electronic trip unit release or solid state trip unit. Let's say LSIG, that means long short instantaneous ground. So LSIG release we want to use here, and the release rating is 160. Let's select this one. Okay, so this is the ABB, this is circuit breaker, molded case circuit breaker, 160 ampere, and minimum delay 0.015 second. And this is this tab, this is the trip device, which is the release. We have already selected the release feature, and this is sensor is 160 ampere. Okay, so here are the parameters for LSIG. So this is L for long time, S for short time, and I for instantaneous. So for this motor protection, let's define this. Let's uncheck this ground right now. Okay, so ALSI, we will use this feature ALSI. Suppose here we need to give the pickup, because this is for just like IDMT 51, IDMT inverse definite minimum time, IDMT 51 overcurrent relay. So this is basically overcurrent relay. If we put the value here, this pickup, LT pickup, then 160 ampere becomes. So 160 ampere, because The motor rated full load current is 123.5 ampere. So we are selecting here 1, so 160 amps. LT band, this is 12, 12.2, let's say 12. Short time, this is 1200 amps. If we use this multiplier 7.5, so it's enough for this setting, because we have the starting current what we have seen for this 75 kilowatt motor, that is almost 755 ampere around this. So this will be enough for this motor to protect. And this ST band in and out, I will show you in the TCC curve what is the impact of this. And this is instantaneous setting. So let's quickly move to the TCC curve. So what we can do, we can add this in the, we can append. You see this feature, start view manager. We can append this one, that means we have added. Okay, so we have added this curve. So this is the curve. Let's turn off this instantaneous function. So LS we are using, either we can use LS for this motor, or we can use L and I. S will be disabled. So in this case we are using this L long time and short time feature. So here let's understand better here. Okay, so this curve, if we want to give the color here, so this is phase, use this one. Okay, so this is the motor protection, curve, and you can see clearly this is nicely suited over here. So this motor starting curve at 80% voltage, and this is 100% voltage. So it is coordinated very nicely. You can see this is in between the motor starting curve and this hot withstand curve. So in between, this is the long time characteristic, and this is short time characteristic. One thing I want to show, what is the impact of this ST band I square T out. Okay, if it is out, that means this is L shape, this instantaneous or this short time feature, this is L shape, this corner. If you in, that means IDMT characteristic, that means inverse, not IDMT, this is inverse characteristic. So on, then the shape will be like this corner will be like this. So in that case, maybe the upstream incoming circuit breaker, that will also to be like this. That inverse property may be required to turn on. So since it is not affecting our motor starting curve, let it be kept open only like this. So this is fine for this motor. So we can say this 75 kilowatt motor is coordinated with this release LSIG release circuit breaker, which is molded case circuit breaker with ETU, electronic trip unit. If we can we can try with another setting also, another trip feature. Instead of electronic trip unit or solid state unit, if we use this thermal magnetic curve as well. So if we use this thermal magnetic curve, so thermal, this part is thermal, this part is thermal. So this is responsible to protect the motor from overcurrent, and this lower part, this lower portion is responsible for the short circuit protection, which is provided by this magnetic setting. So thermal is for overcurrent or overload, and this magnetic is for short circuit. So if you can remember, the motor full load current is 123.5 ampere, so it is less than that, so we need to increase this one, maybe 85%, 136, so that it will be clear. So now the curve is clear, this thermal curve is set finely, and here 12 atms, this is enough, this 8 is fine for the short circuit protection. Okay, so this is another protection. If you use the thermal magnetic feature of the same circuit breaker release, then the motor will be protected. So in that case, maybe here is slightly, let's see if there is no overlap. There is no overlap, this is not touching, still it is very close to this. So in that case, depending on the situation, what you can do, you can switch off this asymmetrical factor. You can consider 1, so that it will be straight line like this. Okay, one more thing, let's see for this solid state trip unit what we have set. Okay, so I think I need to define once again. To define, so it was 1, I think this was 12, I already set this one, and this one 7.5. okay, square out. So this was the setting for ETU, and for this if we turn off, let's see what's the impact of this long time and short time. If we turn off this short time curve, so this is the long time curve, but it is not properly coordinated with the starting curve. So this shape is like this. That's why we have used this short time curve also. If we turn off this long time for better understanding, this is the short time curve, this is definite time, just like IDMT feature, that definite time curve. So this is providing the short circuit protection basically. So we are using the combination of these two, long time and short time, so that it is properly suited in between the motor starting curve and hot thermal resistance curve, and it is protecting the motor from overcurrent or overloading and the short circuit protection. So up to this, in this video we have discussed about the motor protection. We'll continue in the next session.